Welcome to my YouTube channel. If you are joining me for the first time and you have not subscribed to this channel, please, I would like you to do that now. Subscribe, share, hit the notification button so that you'll be notified whenever I post a new video in my channel. And today, for those who have subscribed already, I want to say a big thank you to you. I appreciate you and all that. And I'm going to be looking at the dimensional analysis, still under physical quantity. Now we come to this aspect of physical quantities and units, and that's talking about dimensional analysis. Now, what is dimensional analysis? Here, it is the study of the relationship between physical quantities with the help of dimensions and units of measurement. Now, I've been talking about physical quantity for some time now. Every physical quantity is a dimension. For example, the length of an object is a dimension. Time is a dimension. Mass is a dimension. Speed is a dimension. So the physical quantities we study in physics are all dimensions. And these dimensions, they are different from units. The unit of a physical quantity expresses the magnitude. It gives us the idea of the size of that physical quantity. For instance, if you say that the length of an object is 50 meters, the 50 meters, describe the magnitude of the length and is based on the units upon which it is measured. Because if I have to convert that length to a different unit like kilometer, it will no longer be 50. So units and dimensions are closely related, but there are slight differences between the dimension of a physical quantity and a unit. Now, dimensional analysis is also the process of determining the dimensions of physical quantity in order to check their relationship. The dimension of any physical quantity is an expression that consists the product of symbols, or in brackets, or powers of symbol of the fundamental quantities. For example, the measurement of length has a dimension L. We use the symbol capital L to denote the measurement of length. And mass, we use capital letter M to denote the dimension of length. Now, what is a dimensional formula? The dimensional formula of a derived quantity is an equation that shows the powers to which the fundamental unit must be raised to obtain one unit of that derived quantity. For example, if Q is the unit of a derived quantity and M raised to the power A, L raised to the power B, and T raised to the power C is the dimensional formula, then the powers A, B, and C are the dimensions of Q. Dimensional analysis obeys the rules of algebra. Thus, area is the product of two lengths. So if the dimension of length is L, and then area, which is the product of two lengths, is going to have a dimension of L raised to the power of 2. Volume is the product of three lengths: the length, the width, and the height. Therefore, the dimension of volume is going to be L raised to the power 3. Now let's look at the dimensions of physical quantities. For length, you can see that now the dimension of length is L. We use the capital letter to denote the dimension of length, and it applies to all kinds of length, whether you are dealing with breadth or height or width or radius or diameter or length of a curve, length of an arc. They all have the same dimension, and that is L. M is the mass, and it has the dimension M. Time has dimension T. A current has dimension I. Temperature, that is thermodynamic temperature, has dimension theta. And then the amount of substance has dimension N. And luminous intensity has dimension J. In fact, the dimension of any physical quantity can be written as this, as you can see in this on the screen there: L raised to the power A, MB, TC, ID, theta E, NF, JG. For example, we can write the dimension of length in the form above with A equals 1 and the remaining 6 powers all set to 0. If you make m, the power, that is the power of m is b, if you set that to 0, set c to 0, set d to 0, and so on. Recall that an expression in index form has a power of 0. It is equal to 1. So we need to understand that any physical quantity can be written in that form. Now, any quantity with a dimension written such that all the powers are set to 0, that quantity is said to be dimensionless, and we have a number of dimensionless quantity. Now let's look at the different types of physical quantities in physics. Now we have some that are called dimensional constants. Now dimensional constants are physical values that have dimensions, and then they also have fixed values. Examples of dimensional constants as follows. Gravitational constant is an example, as you can see that there. Planck constant is another dimensional constant. The speed of light in vacuum, permittivity of free space, and also permeability. These are constants that have dimensions. And you can also see that they have units and they have a value that is fixed. So we call them dimensional constants. We also have what we call dimensionless constants. Constants that are dimensionless. Number one, all the trig functions, the sine function, the cosine function, the tangent functions, and their arguments, that is the angles, of these sine, cosine, and tangent, are all dimensionless. Exponential functions and their exponent. An example is y is equal to exponent x. They are all dimensionless constants. How about the logarithm functions? The plane or pure numbers, including pi, they are all dimensionless constants. Then we also have quantities. Dimensionless quantities that have units but no dimension. Example is angles. We can measure angle in degrees, in radian, in gradient. So angles have units, but they have no dimensions. Then we have the dimensionless variables. They are physical quantities with values that may vary, but these ones have no dimensions. They are called dimensionless variable. The strain that is produced in a material, recall that strain is the ratio of extension over original length. Both of them have the same units, and therefore strain has no dimension. How about refractive index? The refractive index of a material, is the ratio of the sine of the angle of incidence to that of the angle of refraction. It has no dimension. How about relative density? In fact, when two similar quantities are compared, the result is that they have no dimension. When we're talking about relative density, we are talking about mechanical advantage, velocity ratio of two distances. It has no dimension. So the fact that when two quantities are compared, quantities of similar nature, the result is that they have no dimension. They have no dimension. Dielectric constant, coefficient of friction, they are all dimensionless variables. We also have variables that are dimensional. We call them dimensional variables. They are speed, velocity, acceleration, force, work, energy, and power, and so on. These dimensional variables, they can take on different values and they have units. So also call them dimensions. So we call them dimensional variables. Furthermore, physicists always place a square bracket around the symbol of a physical quantity to represent dimensions of that quantity. For example, if I demand the dimension of area, I'm going to place A in a square bracket and then I equate it to L squared. So whenever the quantity is enclosed in a square bracket, it means that we require the dimension of that quantity. Look at volume. Volume, the symbol is V. If I need to write down the dimension of volume, I have to place that volume in a square bracket or in square brackets and then equate it to L cube, which is the dimension of volume. Now, the concept of dimensions in physics and its applications in science and engineering is extremely significant. The addition or subtraction of two physical quantities makes sense only if the quantities have the same dimensions. For example, just that we cannot add 4 apples to 3 oranges. And then what do you call that? You say you have 7 apples or 7 apples, oranges. So it's impossible to do that, practically speaking. The same thing applies in this dimensional analysis. We cannot add quantities of different dimensions. That's the essence of studying dimensional analysis. You can't add speed to distance because speed and distance are of different dimensions. Likewise, you can't add mass to force. The mass of a body is quite different. It's a different dimension than the force acting on the body. So any mathematical equations, any physical equations must be dimensionally consistent, that is, must be dimensionally correct. And suppose, for example, we have this equation, A is equal to B plus C, or for A to be equal to B plus C, then it means that A, B, and C must have the same dimension. So, in a nutshell, we can add dimensions, or we can add quantities that have different dimensions. Now, it is worth noting that units of physical quantities are not the same as dimension. I mentioned that earlier. However, it is worth noting that this approach, the dimensional analysis, cannot be used, will not help you to determine the dimensionless constant in an equation. For example, the equation for kinetic energy is half mv squared. You'll be able to use dimensional analysis to show that kinetic energy is equal to mv squared. mv squared is dimensionally consistent with energy, but the method, the approach, will not help you to find that constant half. The same thing applies to the period of a simple pendulum. The period is given by 2 pi square root of L over G. The dimensional analysis will help you find or to determine or to establish that the period is equal to the square root of length over G, but that cannot help you find the value of 2 pi. So these constants in these 2 equations I've mentioned can only be recovered, can only be discovered by experiment or by theoretical means. Number 2, we cannot derive equations containing trigonometric, logarithm, or exponential functions. We may use other means to derive this equation, not this approach of dimensional analysis. Now, this method or strategy becomes difficult when a physical quantity depends on more than 3 other quantities. Now, suppose a constant, in some cases, a constant of proportionality may have dimensions. And sometimes it also becomes difficult to use this approach to determine the value of that constant. For instance, in Coulomb's law, the force applied or the force between 2 charges is given by the product of the charges and then divided by the separation between them. The constant K is 1 over 4 pi epsilon naught. Now, this approach of dimensional analysis will not be relevant here in determining the value of 1 over 4 pi. In my next video, I'm going to discuss the applications of dimensional analysis and then solve problems, very practical problems that you can come across in your exams, whether NECO or WAEC.